Welcome to the first course of the 4-course series in Responsible Generative AI. I am very excited to be part of your journey on building the necessary knowledge and skills to responsibly develop, use, and govern generative AI systems. Generative AI technologies can bring many possibilities and opportunities for both businesses and individuals. But these systems can also have significant impact on business, society, environment, and future of work. Such impactful technologies demand responsible approaches and ability to critically analyze the implications for informed decision-making and to govern for the best results. In the rapidly changing landscape of technology, use case, and governance approaches, I hope to bring the foundational knowledge to decision makers, developers, and end users. My name is Merve Hekak. I'm a faculty member at University of Michigan, teaching data science ethics at School of Information and advising on responsible AI and data at Michigan Institute of Data Science. I'm also the president of a global independent research and education nonprofit, Center for AI and Digital Policy, where we engage in global AI policy work and educate future AI policy leaders in more than 80 countries. In 2022, millions of people were introduced to generative AI products, which promise to transform industries for the better and provide innovative tools to mainstream users. Previously, AI systems were mainly predictive AI, focusing on analysis of datasets to complete tasks such as classification, recognition, prediction, recommendation, etc. Generative AI systems, on the other hand, analyze underlying patterns in data and allow users to create new content based on text, image, audio, video, or code, or a combination of these modalities. The content that you can create is pretty much limitless, and many new use cases are being introduced every week. The adoption of generative AI was boosted by the fact that you only need natural language to use it. However, the development, deployment, and use of AI also brings a lot of new challenges and questions to the table while amplifying the existing risks. So how do we, as individuals, businesses, communities, benefit from this emerging technology? We need all hands in. It is exciting times, and we probably do not know right now many of the applications that will emerge from generative AI over time. We need collaboration between a variety of stakeholders, and we need to promote human dignity, contribute to positive societal transformation, and protect the environment in the process. This is where responsible and trustworthy AI and generative AI comes into the picture. We all have a voice, and as AI developers, users, investors, scientists, policymakers, civil society, we all have a responsibility. Responsible AI means ensuring justified trust for AI technologies. Trust increases the adoption rates, use cases, and investment and research. Generative AI can be transformational for the better, but we need to understand better the possibilities, limitations, and align our focus accordingly. Some may choose to focus on short-term economic gains and exploit data, labor, and natural resources, which would eventually doom this technology, with significant impact on our societies and businesses. Or we can develop and deploy systems with multiple stakeholders and communities in mind, critically analyze the benefits and implications of these technologies. We can work on guardrails to fight against bias, polarization, and malicious uses. We can proactively prepare for positive societal, labor, or educational transformations, invest in enhancing accessibility as well as equitable access, incentivize work on common goods, prioritize ethical and social progress, increase data and AI literacy, and ensure fair distribution of economic benefits. Responsible AI is not just one thing, it is what you decide to prioritize and implement. Artificial intelligence, or even large language models, are not new. They go back to decades. In fact, the first chatbot was developed by Joseph Weizenbaum in 1966. However, generative AI systems have captured the interest and attention of many since they have been made available to mainstream users in 2022. The ability to interact with these systems without technical knowledge and simply by using language meant that more people across the society were able to use different products. But what is generative AI? You can think of AI as both the scientific field and as algorithmic systems. Then machine learning, deep learning, and generative AI as respective subsets of each other. AI systems can be simple, rule-based algorithms, such as if-then scenarios. They can be algorithmic models developed to perform specific tasks. Or they can be very complex systems where it becomes very hard to explain or interpret why a certain input produces an output. AI systems are already deployed in many domains in our lives, from recruitment to insurance, financial and credit decisions, home valuations, healthcare diagnosis, weather forecast, manufacturing, or critical infrastructure management. More complex methods are machine learning and deep learning systems. Machine learning refers to algorithmic models where the system learns from the data it uses, rather than explicit programming. ML algorithms continuously detect patterns and relationships and adjust their logic to produce their outcomes. Deep learning systems use neural networks to assess and represent data connections. The deep in deep learning refers to the multiple layers of neural networks where the data passes through and establishes connections. These neural networks can be thought as interconnected nodes organized in layers. Deep learning models extract connections between features and pass that information to the next layer and next until the text is complete. What makes deep learning interesting is it can learn from both labeled and unlabeled data. For example, it can use datasets where images have tags or explanations. In this case, the algorithm uses supervised learning. But these systems can also learn from datasets even when the data is not labeled and come as raw content. This is unsupervised learning. Generative AI systems are trained on very large datasets or corpus of data. Datasets composed of text, audio, video, images, or even software code are used to train generative AI models. Unsupervised learning techniques are used to train the model. In other words, the models are provided with unlabeled data, and they discover patterns and connections without explicit coding from the humans. A generative AI model learns from the existing relations and patterns between words in its dataset. Users can ask the system to create a response or content by using natural language such as English. In response to the user request, called prompts, the system generates outputs in text, audio, video, or code. You do not need technical knowledge to engage with the system. The natural language interaction makes the system very easy to use for tasks where factual information or accuracy are not main concerns. However, you still need domain or technical knowledge to double-check the accuracy of the outcome, especially if you're planning to take action on the output provided. For almost a decade now, deep learning models have been used to generate more and more realistic images and audio. These earlier systems used variational autoencoders, or VAs, With more recent developments, the most popular approaches to generative AI systems are transformers, diffusion models, and generative adversarial networks, or GANs. Transformers, as used in large language systems, are used to predict the sequential output, next token, in the output thread. GANs are made up of two models, a generator and a discriminator. The first model generates a new output. The other one evaluates it against correct or real data. This back and forth between the two continues until the generated versus the real cannot be distinguished from each other. GANs are used to generate realistic videos or audios or deepfakes, but they can also be used to create synthetic tabular data. Diffusion models, on the other hand, generate images by an iterative process of forward and back, where the model is trained by forwarding and converting image into data noise. In other words, the data structure is systematically dismantled. Then, the model sends the data noise, the unstructured data, back to restore its structure and create the image. While computationally more intensive, this process gives the developers more control over the outcomes. Predictive systems are embedded in many applications we currently use knowingly or unknowingly. These AI systems allow us to conduct data analytics tasks, such as looking at past occurrences of an event and then predicting the likelihood of it happening again. Predictive systems can be used to identify objects in an image or video, recommend what kind of news or social media posts you should see next, detect unusual activity with your credit card, etc. Generative AI systems, on the other hand, identify patterns in their training dataset to create new outputs. In other words, the use cases between these systems are significantly different. They are trained by massive datasets without the need to label pieces of that data. For example, if you wanted to identify an image of a dolphin in a picture, you would want to use a predictive system. You would train the system with many pictures of dolphins, many of them with text tags, until the system was identifying the image correctly. But if you wanted to draw a picture of a dolphin swimming in front of a sailboat, you would want to use generative AI systems. The results of predictive models can be evaluated by using a host of performance metrics. If, for example, you provide the system with several images of muffins and other items, and ask which ones are muffin or not, you can verify the results and have an accuracy rate. Evaluation of outputs of generative AI systems is more complex. With generative AI systems, you may prompt the system to create a picture of a warm, delicious blueberry muffin. It is a lot harder to evaluate if what the system has created is delicious looking, or to assess the extra elements the system added in the picture, in this case the fork, the coffee, or the fresh berries. How one person may evaluate the performance and results may differ from others. The quality of the image and whether that satisfies what you had in mind are subjective decisions. If you were using a language model, the performance can be evaluated across tasks. Maybe you can evaluate it identifying false outputs against a grand truth, or laws of physics or chemistry, or etc. Or more subjectively, by assessing the quality of the responses and whether it satisfies the task. Currently, there are a number of language benchmarks that these systems are evaluated against. These can be thought of as standardized frameworks, where the model is tested against standard language tasks, such as paraphrasing or predicting the sentiment of a sentence. Additionally, generative AI systems have a level of randomness when generating an image or next word in a sentence. The results may change every time, even if you use the same prompt. Therefore, the results are less reproducible than predictive systems and harder to evaluate. These general models are made up of billions or trillions of parameters. With currently available approaches, the general-purpose generative AI systems require significant amounts of computing infrastructure and resources to train. As mentioned before, to train generative AI systems, massive amounts of data is required. Current training datasets represent a good portion of the internet. These are collected by scraping millions of websites and their contents, including discussion forums, social media, as well as scraping of large sources such as Wikipedia, patent applications, newspapers, books, movies, YouTube videos, personal blogs, and using a combination of commercial and proprietary datasets curated for the purpose of training. The scraping of such large amounts of internet content means the training datasets contain significant amounts of copyrighted material, public information, as well as data collected from behind paywalls or paid content. Once collected, the dataset is compressed for efficiency purposes. In other words, the model encodes a simpler version or representation of the training data. Ideally, the dataset should be processed to remove illegal, dangerous, or toxic elements, as well as private information. Quality checks should be conducted, and data provenance and changes to the corpus should be documented. Then, with model training, the neural network learns the relationships and patterns between words in its dataset. Once the model learns these billions of relationships, it can generate outputs when prompted. During the training process, the model establishes connections between the data points and analyzes the strength and weight of these connections for its task. These learned variables are called parameters, and they include the knowledge essential to turn inputs into outputs. However, the system may still need further improvement and optimization. You might also want to reduce some of the toxic or dangerous responses. This is where fine-tuning comes into the picture, where the system is asked templates of questions, and then the responses are compared, corrected, and tuned. Human feedback is used to improve the system's responses. Performance evaluations are conducted again before the system is deployed. These metrics may differ depending on whether the system is general purpose or a specific task-based one, or it might differ by domain in which the system may be used. Responsible deployment requires both the developers and the deployers to ensure the system is safe, secure, and trustworthy. The ex-ante, in other words, the pre-deployment impact and risk assessments, should have been completed at this stage. Foreseen harms and risks should be mitigated, and the necessary feedback and response mechanisms should be in place for those unforeseen risks. It is true that we may not be able to know or foresee every single problem ahead of a deployment. However, this does not remove the responsibility for taking all possible precautions for the known and established issues with AI systems in general. Once deployed, any AI system requires ongoing monitoring for performance changes, new use cases, and for the possibility of adversarial attacks. These are not static systems. Their performance may change due to new data, interactions with users, or even due to malicious actors. Training of generative AI model requires several steps. A model doesn't understand the language in the form that we humans use it. To train the system, language needs to be treated in a formulaic way. In other words, all the information in the dataset needs to be converted into a mathematical representation. This is called tokenization. Tokens are what make the language systems work. They are the building blocks. Let's say the model had this sentence in its training dataset. Tokenization process would first split up every word and punctuation into individual tokens, and then assign a numerical ID to each token. Although in this particular example, tokens match words, you can also tokenize on letters or combination of characters, etc. Now imagine the model doing this for every single word in its training dataset. After tokenization, vectors come into picture. Vectors show the numerical representations of the relationships between tokens. The model reviews its dataset to see what words are the most frequently associated with each word. When we plot these relationships, we can see the word embeddings. In other words, the learned representation for words which are similar or associated. Embedding is the plotted vector representation. Now that the tokens and the vectors are assigned, the relationships and how strong they are become clearer. For example, the word dolphin may have a stronger association with the word ocean or fish or shark within the language dataset. Now let's switch to what the system does when we prompt it. When a user gives the system a request, the prompt sentence or the sequence is also broken into tokens. Then the model finds the embeddings which corresponds to these tokens, processed through the layers of neural networks. Now the model has an idea of possible tokens to use as a response and probabilities for each of these tokens. For example, if you prompted the system to write about a dolphin, the system may complete the sentence, one of the dolphins, with the words swam, jumped, turned, rather than texted. It is important to remember that large language models are all about statistical relationships and representations. A single word, in this case dolphin, has a vector representation. All the other words in the sequence have a vector representation, and then the final outcome or the predicted word or the token has a vector. In other words, the system applies vector calculations constantly to generate a response to the user. As mentioned, calculations to predict the next word in the sequence depends on the existing relationships and the strength of the relationships within the dataset. In other words, the quality of your training dataset determines the quality of the responses you will receive. When the system is predicting the next token, the probability of each next token is ranked. The system may be tuned to always pick the top choice. Sometimes this may lead to repetitive cycles and the outcomes are useless. You can adjust the formulation of generated outcomes, where the model can be made to pick lower ranked words or pick up the words randomly from the probability list and still keep some cohesiveness. Randomness here means that if we were to use the same prompt multiple times, we are likely to get different responses every time. One of the technological breakthroughs which allow for more cohesive responses in large language models is called transformers. You might remember from the beginning of the course that transformers are one of the most popular approaches to generative AI systems. Transformers have contributed significantly to the recent developments in generative AI. Simply put, instead of processing input sequentially, transformers can process several sequences in parallel to each other. This allows training of the model to be quicker and larger. What makes generative AI systems and transformer method very interesting is a concept called attention. Instead of only focusing on the very last word or the token, the model can look at a longer range and analyze the input sequence of tokens. It pays more attention to certain tokens or words which are crucial in keeping in line with the context, the pronouns, word-noun relationships, etc. The attention headers help to improve the model's prediction for the next tokens. In other words, the model takes a prompt, encodes a mathematical representation of the prompt, it runs the embedding and probability calculations. Separately, the most important parts of the previous sequence are analyzed for attention headers. Then, both the probability calculations and the attention are combined to create a new representation. This mathematical representation is then decoded to convert it back to natural language. For example, if the word dolphin in the previous example was used in the context of interacting with the animal in the ocean, the attention headers would make that connection and not suggest next word predictions which would relate to Miami Dolphins, for example, a professional American football team based in Miami. Such ability to analyze longer range of words and keep their relationships intact is one of the reasons the outputs of the generative AI systems tend to sound like the system understands the context. The output sounds coherent because the model uses patterns existing in human language. However, the system doesn't have an understanding of context or consequences. It only has the former knowledge of the relationships between words. You may also notice that if your prompt is beyond a certain length threshold, the responses may be less consistent and less coherent. As mentioned before, once the unsupervised training for the model is over, you may still want to improve or adjust the responses for response quality. Some consider tuning as more of an optional element in the lifecycle. However, for responsible development and for good governance purposes, or to improve the system's performance in a particular domain, it should be paid serious attention. Tuning can be thought of as a step to align the outputs with certain rules. Fine-tuning involves more quality data and human involvement. In this stage, the system's outputs are improved through question and answer between the humans and the model. The model is asked a series of questions, and the answers are compared against expected results or the ground truth. Then the system is tuned further. This work may involve significant human labor. Another way to align the system is called reinforcement learning from human feedback. In this approach, humans engage with the system by providing demonstration or samples of preferred responses, or compare different system outputs and rate the results. After human rating, another neural network tries to predict these human ratings and reinforces this on the model. This becomes an iterative process. Many generative AI systems or products will include two types of prompts or instructions. First one is system prompt, created by the developers of the system, laying out in extensive detail how the system should behave, which prompts to refuse, how to respond when such refusal is necessary, and what tone should the overall system take. These prompts or system instructions can be extensive and run in the background of the system. The user prompts, on the other hand, are what is created by the users, those who are interacting with the system. These user prompts detail what you would like the system to do or generate. You may sometimes get a response that the system is not able to respond to certain prompts. These would be the cases where there is a possible conflict between the system instructions and the user request. You can think of system prompts as meta instructions, which rule how users can interact and engage with the system. Although system instructions are designed to avoid problematic behavior of a generative AI system, they are not foolproof safeguards. The best way to avoid or reduce harmful, toxic, or biased results is to invest time and effort in higher quality datasets, continuous monitoring, and safety and security hardening. These system prompts may be confidential and not shared with downstream users. There might be various reasons for not transparently sharing this information, ranging from commercial reasons to prevention of gaming of the system by users or malicious actors. However, in cases where this information is open, or have been extracted from the system, some of the system prompts may also provide insights into the limitations or issues with a generative model. These can be areas where the developers may be trying to patch or contain the system for issues related to copyright, bias, privacy, etc. Now let's look at some of the use cases and emerging possibilities. Generative AI systems have emerging use cases across many industries. For some of these industries, the impact may be transformative. As our understanding of generative AI systems' possibilities and limitations mature, we will have more creative applications. This is not to suggest that generative AI should be applied to every possible business. Understanding how these systems work, their impact on business and society, as well as the possible risks and limitations, will be crucial for where we want to use these systems. In terms of language tasks, we see both personal and business cases. For personal use, generative AI can be used as a personal assistant. For example, users can ask the system to summarize long text or even audio conversations, change the style or tone of an existing text, or even generate text such as emails, essays, speeches in a certain style. Generative AI can be used to search a collection of documents and pull out the elements when particular words are used. Instead of writing long formulas or queries, you can use language to autocomplete tasks within spreadsheets. We see examples of generative AI used for creation of creative content, such as marketing materials, short stories, or essays. These systems can be kickstarters to create new content, or provide the first draft of long narratives, such as blog posts or social media updates, or even brainstorm ideas. However, it is important to remember that the generated content can be inaccurate, biased, or based on copyrighted material. We will cover these risks shortly. In business, some of the possible use cases are using conversational systems to automate responses for customer queries. This is different from previous generation of chatbots, which were more rule-based systems. In other words, the system was programmed to answer in a specific way for limited query types. Other use cases are summarizing comments or certain themes from customer reviews, turning call records into transcripts. Users can also create queries or search scripts to access information easier and quicker rather than searching within large text or audio recordings. Similar to language tasks, generative AI systems can be used for creative purposes in image-related tasks. The simplest use case is when a user generates new images by simply prompting the system with what they would like to see in an image. These can be as simple as creating a coloring book, or as complex as creating consistent characters in cartoon series, illustrated storytelling, or creating sci-fi imagery, etc. Similar to language, these images can be tailored for specific styles, genres, or themes. In other use cases or possibilities, the system can use a given image and extrapolate or adjust the background of that image, complete the missing or fractured pieces of an existing image, overlay objects from different sources to create a new image, or even enhance existing image for different photographic qualities. In addition to creating still images or drawings, generative AI systems are also used for creating new video segments, animated avatars and animations, or even generate simulations of 3D models of product or design ideas. The importance of using generative AI responsibly and understanding the capacity of these models becomes very important in the video context. While the majority of the videos are expected to be for fun or legitimate business purposes, we are already experiencing very realistic deepfake videos used to create disinformation and sow distrust or blackmail individuals. We will cover the impact of disinformation and deepfakes in the following course. However, remembering that there are always both positive and negative uses to these technologies can already start us in the right direction.
Generative AI systems can be used to create speech from image or text input, to generate music or audio elements, synthesize sound or voice, or build sound effects. These systems convert text into audio transcripts, for example, to use in audiobooks. They are also used for assistive purposes, and can, for example, convert an image to an audio description by explaining the details of an image to a user. The models can also be trained to mimic the voice and style of a person from a recording, which can be used for voice-over or dubbing or translation into another language. While this might be used for creative purposes, the capability also opens up possibility to create audio deepfakes or potential fraud scams.
Just like the language tasks, code generation with the systems is based on the codes included in the system's dataset. In other words, the system's outputs will be only as good as the quality of the code in its dataset. Coding can be used to build games, complete tasks, or create websites. And it can be as simple as prompting the system with instructions or drawings of what you would like to code. You could, for example, use Gen AI to first create a game storyline, then the game character personas, then their animated avatars, and the code could then be generated to turn these ideas into an actual game. The system can be prompted to create software code in a particular programming language, or used to explain and troubleshoot coding issues, or even help with documentation of coding. You can prompt the model with the error code you're getting in the code and ask it to explain the issue and suggest corrections. While using Gen AI for coding can be a great way to kickstart your project, it does not remove the need for domain and coding expertise required to double-check the code or the need to secure your model from adversarial actors. The issue with text hallucinations can repeat itself here too. The system may generate inaccurate code or include malicious code learned from its training dataset. Just like deepfakes, malicious actors can more easily create adversarial codes with these systems too. A less known and discussed application of generative AI is time series analysis. This approach may be considered as a research question for the moment. It uses timestamp data, or measurements, collected over a period, and is used to understand the behavior or trend of the system. One challenge with using time series is the temporal, or time dependency between the features, as well as the possibility of other factors contributing to changes. Consider continuous data such as weather patterns, energy consumption, stock market, network activity, sale figures, traffic or logistics data. Just like word embeddings, which show words that tend to appear together, time series datasets can be analyzed to understand the patterns between the features, such as co-occurrences, seasonal or periodical changes. Researchers are also working on whether GANs can be used to create synthetic data from existing time series. In other words, creating sequential data, or the possibility of extrapolation, where data might be missing for a certain period of time. If time analysis works as expected, it can also be used for scenario simulation of patterns and interventions, or detect anomalies or deviations from the pattern. Some generative AI systems are trained on a single type of input, such as only image or only text. Therefore, their outputs are limited to a single input type. More complex multimodal generative AI systems, on the other hand, are trained with input from a variety of types, such as text, image, or code. The models analyze the associations between text and other types of data, such as the corresponding image or audio, and it can generate outputs in different formats too. For example, you can prompt the system with an image and then ask the system to provide further information about the object, or upload a hand-drawn template of a website and ask the system to create that website for you. Or you can use text prompts to create videos, now using diffusion transformer approach. The limitation is when the instructions are too complex or when the response requires spatial or logical reasoning. Developing and training generative AI models from scratch is resource-intensive work in terms of talent, money, computing power, data, and effort. Currently, only a handful of companies are able to develop and train base models. Many downstream users or businesses build their own models on top of these large base models. However, whether you're building the model from scratch or building a connected or dependent model, there are certain risks you should be aware of. In the following section, we will cover some of the general risks related to the foundational elements of these systems. At the simplest level, large language models pick the next word in a sequence. What the model is essentially doing is just asking over and over again, given the text so far, what should the next word be? The responses are based on statistics and reflect the most frequent word connections. Because the model is based on statistics rather than logical reasoning, these systems can produce inaccurate results, and with high confidence too. They can reflect what is in their dataset, but cannot deduct logic or an independent understanding of the world. This means they may have incoherent or wrong responses to prompts involving nuanced contextual knowledge, idioms, spatial explanations, or causal reasoning. Furthermore, the quality of the training dataset, whether it is representative, recent, sufficient, can also impact the model's ability to make better generations. When used for creative tasks, such mix and match function can be helpful and even preferred. It is considered as a feature rather than a bug by some developers. However, for any use case where the accuracy, factualness, or precision of output is important, decision makers should think twice about using generative AI systems. Although generative AI systems are great in creating coherent sounding outputs, these models do not have the technical means to complete complex tasks where nuanced understanding of issues is necessary, such as financial or legal analysis. The providers of these models warn against these inaccuracies in their terms and conditions. Depending on the use case, these inaccuracies could cause significant harms or failures for both the individuals receiving the prompt as well as the businesses whose system is producing such outcomes. Liability issues can emerge for businesses. For example, a recent study by Stanford researchers showed that when language models are prompted for specific legal queries, their inaccuracy rates range from 69 to 88%. These models do not correct the errors even when prompted further and tend to reinforce incorrect legal assumptions and beliefs. This may be a relief for some paralegals and lawyers concerned about their job security. However, imagine a person who doesn't have the financial means to hire a lawyer and decides to use a language model for legal questions, to write their plea, or even understand the legal process. The same study also warns about tendency of language models towards overconfidence, irrespective of their actual accuracy. Similar warnings can be made for any task that may involve the user taking a real-life action as per the responses of the generative AI systems, such as making financial investments, medical inquiries, and even planning your next vacation. But even when you least expect it, or with personal use of generative AI systems, there are still serious considerations we need to keep in mind. Ideally, if there is a benefit from these emerging technologies, we would want them to benefit everyone equally and equitably. However, in some cases, the generated outcomes may be inappropriate for the context, sometimes even outright offensive. In many cases, it is the decisions about training data sources and the decisions about the design which go into the model which result in biased or toxic results. Some AI products are designed to avoid certain issues by way of system prompts or meta-instructions. However, such restrictions on certain content may also account to censorship. The target issue may be culture or context dependent, or it might be a politically divided issue. In an attempt to create safeguards against a certain content, the system may be trained to avoid certain words or language in prompts. However, this may result in users not being able to generate outputs to express themselves freely, create content for their products aligned with their identity. Although it is possible to use different prompting techniques and make the system generate the censored text or image, the extra step or burden, or possibly violating terms of use, are still problematic. Using prompt refusals as the only mechanism to fight against toxic content or inaccuracies may result in a false sense of assurance for the developers and deployers of the system. When large chunks of internet is scraped, the datasets may also include illegal or offensive imagery from the web, such as violence, hate symbols, pornography, and more. Researchers analyzing samples to detect hateful content also found that while generative multimodals are scaled up with larger and larger datasets, the hateful content, the negative stereotypes, and other harmful representations can appear at a significantly higher rate in larger datasets. Just because a training dataset or even a product is widely used does not mean that it is free of toxic, illegal, or private data. Unfortunately, many of the generative AI systems available as products or open source do not have associated data quality or provenance documentation. This means we do not know the extent of public versus private information in the training dataset, free versus copyrighted material, the extent of bias in representation, and toxicity. When using these models for personal or business purposes, generated output should be treated with caution regarding its provenance, accuracy, and related risks. Not being able to analyze the dataset and the models also means that we are working in the dark about the capabilities and behavior of these models. As an example, reporters in Washington Post have analyzed Google's C4 dataset. This is a dataset which is widely used for training purposes and reflecting contents of 15 million websites. The dataset is reported to be used for several large language models too. You will notice that some of the sites used can be more neutral and credible sources of information, such as patent database, Wikipedia, etc. However, data sources also include websites which have information such as voter and address registries, or scraped websites where individuals or even companies provide exclusive content for a fee or subscription behind a paywall. A certain subset of the dataset shows propaganda sites and discussion forums engaging only in certain political or worldviews. Quality of the training dataset makes significant difference in the outcomes generated by AI. We have more information about this dataset in the example. However, this is not the case with many generative AI systems, where vendors do not share the details on the provenance or the quality of the data. Gender bias and stereotypes in language and image models are not new. Previous work by scholars such as Dr. Safiye Noble or Dr. Aylin Çalışkan have shown that datasets containing unrepresentative or skewed data points can result in amplifying existing societal stereotypes. Dr. Noble's work provides evidence of racialized and sexualized images associated with Black and Asian females in web search results. Dr. Çalışkan and co-researchers' work shows how language corpus can encode social biases into word embeddings. For example, frequencies of words associated with man versus woman may result in certain professions or tasks being associated with males versus females, let alone the binary approach to such representation. These biases and stereotypes naturally extend beyond gender and sexual orientation representation. They can be found in many cases where identity or location are involved, such as religion, ethnicity, race, ability, etc. Such bias and toxicity becomes more problematic when these systems are deployed beyond academic research. They become part of people's everyday lives, their way of self-identification and representation. They are sold as products, respecting consumers. Yet, users may experience a variety of harms, ranging from not getting responses which reflect their prompts, or having to deal with outputs which portray their identity as toxic or violent. Some companies acknowledge that training datasets contain such harmful content. For example, OpenAI shares in its product documentation that, quote, known risks associated with language models are still problematic, and GPT-4 can generate potentially harmful content, such as advice on planning attacks or hate speech. It can represent various societal biases and worldviews that may not be representative of the user's intent or of widely shared values. It can also generate code that is compromised or vulnerable, unquote. The system card documentation continues to caution that, quote, the model has the potential to reinforce and reproduce specific biases and worldviews, including harmful stereotypical and demeaning associations for certain marginalized groups, unquote. In addition to responsible development and training of these models in the first place, it is important that training datasets can be analyzed by academic researchers or interested parties for data provenance and toxicity. This means that businesses developing these major systems could share information on managing AI risks with industry participants, academic researchers, governmental agencies, and civil society experts. They can publicly report AI systems' capabilities and limitations, including safety evaluation and bias. Such information sharing can also allow the downstream businesses who are interested in building their products connected to these generative AI models. Knowing the data provenance and quality allows these businesses to meaningfully assess the risk that they are taking. Image generators can also reflect the stereotypes and dominant worldviews represented in their training dataset. Just like language corpora, image models are trained by scraping large parts of the internet, including sources like news, discussion forums, social media posts. They detect patterns in this corpus. The model associates the image with its respective text tag or caption. In doing so, the model may associate negative actions with certain groups, ethnicities, or religions, deepening existing stereotypes. This bias can also manifest itself in different ways. Bloomberg, for example, recently conducted an analysis of more than 5,000 images created with a generative AI product. They showed the results in terms of racial and gender disparities. Their work warns that the system is not only biased, but possibly biased worse than the real world. You might have heard that AI bias is a reflection of bias and inequity in our societies. However, if not responsibly developed and deployed, biased AI systems can also amplify the bias and expand the equity gap. The Bloomberg reporters generated thousands of images related to job titles and crime. They prompted the text-to-image model to create representations of workers for jobs that are typically considered high-paying or low-paying in the United States, plus 3 categories related to crime. For each image generated, they calculated an average color from the parts of the image that made up the facial skin. Every image was then reviewed by a team of reporters and labeled according to the perceived gender of the person pictured. When considering bias in terms of both skin tone and gender, men with lighter skin tones represented the majority of the subjects in every high-paying job, including politician, lawyer, judge, and CEO. Images generated as response to low-paying job titles mainly represented darker skin tones. For each image depicting a perceived woman, the system generated almost 3 times as many images of perceived men. Most occupations in the dataset were dominated by men, except for low-paying jobs like housekeeper and cashier. In another instance of stereotypes and imbalanced representation in the dataset, a group of researchers prompted one commercial image system with, quote, "Black African doctors providing care for white suffering children," unquote. These researchers, working on a broader study of global health images, found that despite changing the prompts or being specific with the request, the model almost always depicted the children as black. When the doctor's image seemed to reflect a black African doctor, this time the image generator added objects such as giraffe or vaccines into the image. As mentioned before, generative AI systems are trained on very large corpus of text, image, video, code, and audio, where this corpus includes data scraped from the internet. The data includes copyrighted material, as well as private sensitive information, or even proprietary data. When a user prompts the system to generate an output, the private or sensitive data contained in the training corpus may be exposed to other users. Another consideration is when user prompts are repurposed to further train the model. When engaging with the system, the user prompts and documents uploaded into these language models can become part of the training dataset by default, unless the user opts out. Such information then can be exposed to other users. Some product settings by default start with using prompt data to train the model, but then give the users the option to opt out. With increasing adoption of generative AI products, many public and private entities are concerned that their data may be ingested and then exposed unintentionally. We have seen new internal policies warning employees against uploading any private, proprietary, or corporate data into these products. In addition to data protection, privacy is also a serious consideration when using generative AI systems. The massive amounts of data scraped from the internet, as well as the proprietary datasets, means that many distinct points of information on an individual can already be included in the system, such as home address, phone number, employer, professional title, voting behavior, educational background, location data, etc. In fact, some models can provide precise location of their users. Data privacy means a user can and should have control over their data. However, with current design of many language and image systems, data is collected without informed consent, and the products may not allow any control over private data in the system. The user may not be able to access information about them in the system, or have the means to request correction or deletion of their data from the training dataset. Additionally, some of the generative AI image products can be used to identify a person. In other words, upload the image of a person and get extensive information about them. These issues might be more controllable in systems where privacy by design is adopted and modern privacy enhancing technologies are used. Generative AI system training data includes public and free data on the internet. It has also been shown through prompting, red teaming, and academic research that these systems are built upon significant amounts of copyrighted material. Copyright protections or infringement is a hotly debated topic across many jurisdictions. Depending on who you ask, there are many arguments in this conversation. On the vendor side, some argue copyrighted material is only used to train the system and extract relationships, and that the system is using mathematical representations. Some others argue that they indeed use the copyrighted material, but that the use is fair and legal. Meanwhile, creators, authors, publishers, actors, or even code developers whose work is being used without their knowledge argue that their work is used for commercial gains, that they did not consent to the use of their intellectual property, or the reproduction of their styles, or even their own image and likeness. Where the courts will land on copyright and trademark questions is a complicated issue for the moment. However, for businesses interested in integrating generative AI into their operations, for example, use generative AI in their organization to engage with clients, or use creative content, the possibility of infringement is a serious consideration. The business may unintentionally end up using unauthorized material. Just like any other technology stack, generative AI systems are also vulnerable to adversarial attacks. There are many emerging ways generative AI systems can be attacked. Machine learning technologies are vulnerable to attacks which can cause them to fail, sometimes without the user even noticing the failure. The attacks can be conducted both during the training of the model as well as after deployment. These systems may be corrupted throughout their life cycle. Adversarial actors will continue to find holes in security systems. This necessitates ongoing monitoring and continuous security response. Suffice it to say that we do not know all the ways the system can be attacked or how the outputs may be manipulated. Adversarial actors will continue to challenge the integrity and quality of the data and cause unpredictable or harmful responses from the models. There are several adversarial attack types relevant to generative AI models, such as prompt injection, also known as jailbreaks, evasion and extraction attacks, data poisoning, and those resulting from vulnerable components. Let's cover a few of these in more detail. In prompt injection or jailbreak attacks, an actor can use inputs or prompts to manipulate the behavior of large language model, leading it to expose data or process unauthorized action. Jailbreak is when an actor uses a variety of crafted prompts to inject instructions or code to the system so as to break the controls or restrictions the system was designed. In other words, break the rules laid out in the system prompts or instructions. The actor may make the system ignore its limitations, restrictions, or rules, or even make the system take on a new persona which can respond to prompts without any rules. When the attack is done at plugin level, other users engaging with the system may not be aware of the attack and accept the outputs of the system as normal. For example, an attacker may inject a prompt in the system to always prioritize a particular brand's content in the outputs. Other users may take that ranking as natural and not as a result of an intentional attack. Malicious actors may also use prompt injection techniques to impact the availability of generative AI system, or the time it takes to generate an output. If you're interested in using generative AI system in use cases such as virtual assistants, content moderation, or chatbots for your organization, it is necessary to make that decision based on a good understanding of your business needs, as well as issues of bias, inaccuracy, and possible attacks on your system. These language systems can be prompted to make the system provide abusive, racist, or toxic responses, or with responses which may incur reputational or financial loss to your organization. With evasion attacks, an actor attempts to alter how the model responds to an input. In other words, the actor tries to prevent the model from correctly identifying the data it is analyzing, and hence evade the task that the model is supposed to perform. As a result, the model provides inaccurate results. Evasion attacks have been an unresolved problem in machine learning systems used for classification or identification purposes as well. For example, by adding noise in the data, or even a physical object next to the image, facial recognition or object detection systems can fail spectacularly. For generative AI, researchers show that even adding a very small noise in the prompt data can cause the system to provide a completely different output controlled by the attacker. In this case, the attacker can control what a voice-to-text transcription system produces at the end. Depending on the use case, altered results can cause economic, reputational, or legal harms. It might also impact the trust of the users in the system's performance. Extraction is when you deceive the model into disclosing its design instructions, private, confidential, or otherwise sensitive information. Prompt injection can be used to attack main models or custom models built on foundation models. One recent study showed that by using simple prompts, the researchers had 97% success rate for system prompt extraction and a 100% success rate for file leakage. In other words, they were able to extract almost all the files and instructions developers had used to build a custom chatbot. For businesses considering to connect to foundation models via APIs, or fine-tuning a general system with business-specific data, instructions or expert knowledge, and securing this information is extremely important. As mentioned before, it takes significant resources to pre-train a generative AI system and conduct regular training on the general models. If the model is not connected to the internet, in other words, able to retrieve current data, there will be a data or knowledge cutoff date. In other words, the training dataset only contains data up until a certain date and does not include information created beyond that date. Depending on the use case, this knowledge cutoff may or may not be a serious issue. Some businesses may decide to integrate or connect the model to real-time data sources and APIs. Some models or generative AI products are connected to the web or even search engine browsers. Such connection removes the issue of outdated data, but may introduce new considerations on managing the quality of data.